Okay, let's look at the 2015 question. First one is simple state, the principle of superposition, and it is when two waves meet, two or more waves meet really. The resultant displacement is equal to the vector, and that's a key word in there, sum of the individual displacements. Okay, displacement is a vector. All that means is if one is having a crest and the other is having a trough, you're going to have to subtract the trough displacement of that from the positive displacement of the crest. And that is a definition that you'll need to learn off. Figure 4.1 shows two waves of the same type traveling in opposite directions that meet in the same medium at the same time. Give one reason why the two waves will not create a standing wave pattern. And what we can see there is, yeah, now that's a bit strange that it doesn't give any information about that diagram. So we don't know whether it's time or, well, it does say same time, so we're assuming this kind of distance on the x-axis, are we? But either way, we can say that it is, they have different frequencies. Okay, or you could say the sources are not coherent. Okay, so to see a recognizable interference pattern, the wavelength or frequencies has to be the same. On figure 4.1, sketch the resultant wave that will be produced when the two waves meet. And all we do is add, so this point here, the grey and black one have a displacement of 0. Here we just add this point, and that will bring us to about there, I would say. This one, add that displacement essentially to that displacement, and it gives us about there, and we just keep doing that as best we can. And you do that at each position, and we end up with a wave like that, and then just draw a continuous smooth line that tries to go through those points. Okay, so your marks for that is the resultant wave has a higher amplitude than the original waves. They cross at the correct point. Okay, so this wave and this wave should cross there, and the last one is resultant correct after crossing point, so that these become negative after that. So 3 marks in total there. The appearance of a standing wave as producing a stretched spring is shown as below in figure 4.2. How many nodes and antinodes are there in the standing wave? Well, let's label them. There's node, 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 node. Count them up, and it is 7. Number of antinodes then go in between, and we get 1, 2, 3, 4, 5, 6 antinodes. Okay. The frequency of vibration of the string is set up, the standing wave is 70 Hz. The distance between two adjacent nodes is 15 centimeters. Calculate the lowest frequency of vibration that would set up a standing wave on this string. So what we're saying is that on this diagram, between there and there, to say nodes or antinodes, doesn't really matter because it'll be the same. 2 adjacent nodes, so yeah, let's go from here to here is 15 centimeters. Now that's half a wavelength, so full wavelength then is going to be 30 centimeters, okay, because that is a full wave. So we put in lambda equals 30 centimeters for the wave that's shown in the diagram. F is equal to 70 hertz. Do V equals F lambda. V equals, let's make that 0.3 meters times 70. V equals 21 meters per second. Now, as long as we don't change anything else about that string, that velocity is going to be constant no matter what the frequency is here. So we've worked out the velocity for that string. Now we need to calculate what the frequency is. Basically for our first mode, okay, the lowest frequency. So V is still 21 meters per second. So to find F, we'll need the wavelength. Now, if we look at our diagram again, and I'll maybe go over here. In the first mode of vibration, it's going to vibrate like that, okay? In such a way that we have half a wavelength, but the distance between the first node and the last node, if we count it out, well, between there and there is 15, and we have 1, 2, 3, 4, 5, 6 of those. So that distance there is going to be 6 times 15, which is 90, is it? Let's see, 6 times 15. Yeah, it's 90 centimeters. So the total length of our string is 90 centimeters. But that means that half a wavelength when we're in our first mode is 90 centimeters. Therefore, lambda is 180 centimeters, or 1.8 meters in our first mode. And we just go back down and plug that into this equation. And we do V equals F lambda. 21 equals 1.8 F. 21 divided by 1.8 equals F. And 21 divided by 1.8 should give you 11.6 reoccurring, so we'll round that up to 11.7 hertz. Now, you could have also done that by kind of recognizing that this is what the sixth mode of vibration, and therefore the sixth mode of vibration is equal to 6 times F1. Divide your frequency there, which was 70 hertz for that one, divided by the 6 would give you the same 11.7 hertz for your F1. But this way, kind of going through first principles, it's a lot of work for 2 marks, but I think you're less likely to make mistakes with that.